Thanks for downloading a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online. Now stay tuned for your 3CR podcast.
Welcome to another episode of Lost in Science, and boy howdy do we have an episode for you today. My name is Chris, and I am very excited, as is most of the astronomical and astrophysical community. Why? Because of the latest gravitational wave observation. Gravitational waves, remember, are those ripples in space and time caused by cosmological events out in the universe, big collisions between things like black holes and neutron stars, which is the latest observation. Yes, this discovery that won this year's Nobel Prize in Physics has now achieved yet another amazing success with an observation of neutron stars colliding that, as I will explain, has revealed so much about our universe, confirmed some theories and taught us some new things. And speaking of totally unexpected things, Stu this week is talking to Chloe Plett from Curtin University in Western Australia, who has discovered a ichthyosaur fossil, that's an extinct prehistoric reptile, with soft tissues in its fossils. This is like blood and cholesterol, red blood cells, white blood cells, and other elements of blood, revealing more about the biology and the diet of these extinct reptiles. Exciting science, all coming up on this week's Lost in Science. On with the show.
Science, the final frontier. These are the voyages of Lost in Science, our ongoing mission to explain strange new words, to seek out new science and new explanations, to boldly go where no radio has gone before.
Yes, you're listening to Lost in Science. My name is Chris. And Stu, do you remember when the first gravitational waves were detected?
Yeah, this was last year or the year before? I can't recall.
It was
exactly.
February 2016 it was announced.
Yeah.
And yeah, it was astronomers were really excited. I think they managed to generate a fair bit of excitement around the world, saying that this would be a new era in astronomy, and everyone else shared that excitement and felt really good for them. But I'm sure that most people thought, I don't quite get what's the big deal.
Don't really understand what a gravitational wave is.
Yeah, but also even how is this going to show you new things? Like what actually is what is it going to reveal? And well, we do have an answer now. We have a new discovery that has given us fantastic insights, and it shows the power of this new era of astronomy.
So what's happened?
This is the detection just recently of colliding neutron stars. They were first detected by the gravitational waves and then using the entire electromagnetic spectrum. And this single event has taught us so much about our universe, and it's fantastic.
So they detected the gravitational waves from two colliding neutron stars, and then what? They were alerted to the fact that there was two colliding neutron stars and honed in and watched them further? Or
yeah,
is
pretty
that what
much.
happened?
So look, I'll give you a bit of background. So February 2016, they announced their first discovery of gravitational waves, the actual detection using the Advanced Laser Interferometer Gravitational Observatory, or LIGO. And this won the Nobel Prize in Physics for this year to three of the main people involved, which was Rainer Weiss, Barry Barish, and Kip Thorne. But that was colliding black holes that caused that signal that they saw then. Since then, there have been three other observations of colliding black holes, which, black holes are pretty big and they make big collisions and they send big ripples throughout space-time. But the problem with black holes is well, being black, there's not much to see.
You can't. There's nothing to see because all the light gets sucked into them, and that's the whole point, isn't it?
Yeah, exactly. So neutron stars which are smaller than black holes, they were kind of the main game. So a neutron star is basically, it's a leftover from a supernova generally. So a massive star, many times the size of the sun, explodes and its core collapses under its own gravity. The gravity gets so strong that the electrons are pulled into the nuclei of atoms, and you're basically just left with neutrons making up this neutron star. So they can be about the size of a small city, roughly, in diameter, but they weigh more than our sun.
So they're quite small as stars go.
They're very small and very, very dense.
But quite massive in terms of how much they weigh, I guess, if you wanted to think of it as weight. But,
exactly.
Yeah.
They often also, a lot of stars are found in binary systems, and particularly these very massive stars that form neutron stars are often found in binaries. And so when the binary neutron stars orbit each other, they actually eventually slow down. Well, so they lose energy, giving off as gravitational waves, which is what we detect, and eventually they will spin into each other and collide, which is what we detect.
So the gravity of the two stars pulls them together.
Yeah, they're orbiting each other, but what's actually happening is they're losing energy in the form of gravitational waves. Just by their orbit, they're giving off gravitational waves, and this is energy being lost in the system. So normally, without that, then the orbit would go on forever.
Okay.
But the fact they're losing energy makes them fall into each other. So this was the theory, at least. And the idea is we would see this, we would basically see the radiation that they give off when they collide. Then on the 17th of August 2017, LIGO and another observatory, there's been another one come online since then, the Advanced Virgo Detector, which is based in Italy. It's a European collaboration. Both observatories detected a signal that matched this prediction for neutron stars. And so what they did is they sent out an alert to select members of the astronomy community, basically saying, look to the stars. And everyone did. But before they did that, they didn't have a chance, because 1.7 seconds after the gravitational waves were observed, the Fermi Gamma Ray Space Telescope detected gamma rays, a gamma ray burst. This is a very short burst of high energy gamma rays. These gamma ray bursts had been observed for a long time. The theory was that they came from these colliding neutron stars. So this was a nice confirmation that that's actually where they came from. So that was just a little thing that happened on the side while everyone was kind of waking up to the idea that there was this collision. Meanwhile, so then astronomers from around the world, they all pointed their telescopes at the spot in the sky, because we had these two different observatories, different parts of the world. We were able to triangulate it to a part of the sky. It wasn't a very narrow down part of the sky. It was still about 150 times the area of the full moon. It's a fairly big area to search. But it took less than a day for someone to notice something. This was the 1 meter 2 hemispheres team. They were using a telescope in the Atacama Desert in Chile. They noticed there was a bright object near a galaxy, NGC 4993, which is 130 million light years away in the constellation of Hydra, for those who are playing at home. So once they saw that, this new basically dot that wasn't there, everyone knew where to look, so everyone pointed all the telescopes at this one particular source, and so that was where the money was. And so the light that they saw, that the telescope saw, was something called a kilonova. So not a supernova, not just a nova, but a kilonova. Now,
is that less than a supernova?
Well, it's just a different name. It is kind of less than a supernova, because a supernova is from, I don't know. Okay, so a supernova is when, I said, a star kind of collapses and it blows off its outer layers in a huge explosion. What this is basically the shockwave from the colliding neutron stars ripples through the gas around it, and it causes a whole lot of new nuclear reactions and causes a lot of light and other radiation to be released. Now, this is interesting itself, because because we had this light, we were able to measure the spectrum of the light, and we were able to see what the nuclear reactions were creating. And this is where we found another thing. So we learned about where elements come from in the universe. So as you might be familiar, after the Big Bang, after everything cooled down, we've got some of the lightest elements. We've got hydrogen, mostly hydrogen, but a little bit of helium and lithium and other stuff like that.
Yeah.
The rest of the stuff that we're made out of is mostly made from supernova explosions. So what happens is inside stars you get nuclear fusion reactions that make the heavier elements. When you get the stars get really, really big and they start really, really active, about to explode, they make all these heavy elements, things, and carbon and oxygen and nitrogen and everything.
Don't they sort of expand and contract, and that
they do, yeah.
Just before they explode, they sort of do this sort of pumping in and out thing, and that's when a whole lot
it's
of
all
that
the compression,
stuff,
causes these higher energy reactions. And you basically get everything up to iron at that point. So where do the heavier stuff come from? Because a lot of heavier metals than iron.
Yeah, iron's not the heaviest thing.
And this is where the kilonova comes in. So it has like a much stronger compression waves that goes through. Also a lot of neutrons coming out of the neutron star. And so you get the source of material for all these heavier elements. So they looked at the spectrum from this light, from this kilonova, and they saw that it was making gold.
Gold, baby.
Gold. There was basically as much gold as the entire mass of Earth. That's about 1,000 trillion tons. And so this basically suggests that the gold that we actually have here on Earth was also created in such a cataclysmic event, a kilonova billions of years ago.
Right.
So this is why this thing is so exciting. Look at all the things that we learnt from this one little event. We learnt that we are able to detect neutron star collisions using gravitational waves and triangulate where they are in the sky. We can compare that gravitational waves with the conventional astronomy to learn new things on different sort of types of radiation. We learned that neutron star collisions produce a gamma ray burst, which we didn't really know about. And we learned that gamma rays, basically, they arrived at the same time as the gravitational waves, which tells us that they travel at the speed of light is the same as the speed of the gravitational waves. It means it's probably constant. It probably is the ultimate speed limit of the universe that Einstein suggested. We learned where gold comes from. And we learnt that that we can do all this with thousands of astronomers working on different projects, or coordinate their efforts with lots of different telescopes around the world to discover make these collaborative discoveries. It is absolutely huge.
It is really quite amazing. But one thing I want to know, so this is 130 million light years away.
Yeah.
So it would take 130 million years at the speed of light. There's probably no point going to get the gold, really, is there?
No, probably not. But we know it's out there. The fact that you see this big bright light in the sky and it's like, oh, it's made of gold. That is kind of cool.
That is cool.
I'm Maggie Adair Pocock, and you're listening to Lost in Science on 3CR.
So one thing we do love on Lost in Science is a good story about fossils. And I guess most of us think about fossils as being, bits of old bones or, hard parts of animals that have been preserved one way or another and have turned into effectively rock pressings of what animals used to look like a long time ago. But a recent discovery of some fossil bones in Germany have revealed some very interesting soft tissues contained within the fossils, which is very unusual. And I have got one of the researchers who was working on these fossil specimens, Chloe Plett, who is a researcher at Curtin University. Thanks for joining us on Lost in Science, Chloe.
Hi, thank you for inviting me.
You are based in Western Australia at Curtin University, but these fossils were dug up in Germany. How did you get your hands on them? Who funded the project and who was involved in the collaboration?
The project was funded mainly by an ARC Discovery Outstanding Research Award to Professor Kitty Grice, my supervisor, and we had extra funding from the Institute for Geoscience Research and Curtin University for my international fees. And the conclusion was collected from southwest Germany by my co-supervisor, Professor Lorenz Schwark, who is a German professor, but also in Kiel University, but he's also an adjunct professor from Curtin University. Overall, we did this work in collaboration with various institutions, such as the CSIRO, Kiel University, the John DeLetter Center, and Curtin. Well, basically, there was part of a collaboration. Was one of my co-supervisors during my PhD is an adjunct professor at Curtin University, and he's based in Germany, so he gave us access to those fantastic samples.
Now, these samples were from an ichthyosaur. What's an ichthyosaur?
That's an ancient marine reptile. Like, it's basically looking very similar to a modern-day dolphin, but instead of being a mammal, it was a reptile.
The ichthyosaur fossils that were discovered in Germany, they were fossilized in a very particular way and somehow preserved soft tissues in with the bones.
Basically, it's by degrading the organic matter, superficial organic matter, it changed the microenvironments, and they somehow, at the same time, they degrade it, they preserve it in a very isolated way from the environmental condition, and they preserve it from further microbial degradation or just scavenger degradation and so on.
Okay.
Which is important as well, because those concretions, those microbial carbonates, form only nanoxic environments, almost only nanoxic environments. So you don't really have scavengers. You only really have microbial degradation of the organic matter. That takes longer, and that allows for preservation as well.
So what were the tissues that were preserved in these bones?
Well, obviously the hard tissues, as you mentioned in your introduction.
Yeah.
The bones, like the bone itself, the bone matrix was preserved, the mineral bone. But also, well, we found some collagen fibers and some white and red blood cells, and what we think are platelets, like, as well. So we have various types of blood cells preserved within the vertebra bone. What is interesting is the fact that it's a vertebra. Potentially, that's where the blood cells are fabricated and are produced by any vertebrates. So that was very interesting to find them in situ, if we can say so.
Yeah, it is really, really interesting to actually have tissues like that you can investigate directly rather than just, I guess, guessing what they were doing or how it worked, but you've actually got the samples that you can work with.
Yes, and that's also building on another project from my working group and from my supervisor, Professor Cliti Grice. Before me, she had another student working on carbonate concretion, and Cliti is specialized in biomarkers, so it's molecular fossil. People often talk about morphological fossil, that's what everyone is aware of, but there are also some molecular fossils, and they were very successful in finding the oldest cholesterol and the oldest sterols in a carbonate concretion. That's where that's what we decided to build on, and looking at more recent concretion, and one of those concretion had this ichthyosaur bone in it. And we decided to apply some more, imaging techniques as well. Like, I've been studying the organic matter and the biomarkers, the molecular fossils themselves, and as well the soft tissues.
Right, so, but this gives a sort of a different view of fossils in a way, I guess, looking at the biology of the animals themselves and not just the morphology, as you said. Is there anything in particular about this ichthyosaur fossil that was interesting in its biological or molecular makeup?
Well, yes, obviously we were finding those red blood cells and those white blood cells, finding that is pretty exceptional in itself.
Yeah.
Of this age, it's 180 million years old. So it's a bit more than that. So imagine things being preserved over such a long period of time is like something very exceptional, and we were also very lucky to have such an exceptional sample to work on. The cholesterol itself, we are all aware of cholesterol in our own ways, but the thing it gave us, the information it gave us, is it gave us information on the diet of this extinct ichthyosaur. So in other papers and in the literature, you find ichthyosaur with gut content, so you can literally look at what he's been eating.
Yeah.
But we had the trace of that in the molecular way with the cholesterol, and it's a stable isotopic composition.
So you could actually analyze what was in the blood to figure out what the animal was eating before it died.
That's a bit more tricky than that, but yes, we could see its lipids, could see some of the ichthyosaur lipids, and doing isotopic measurements on it would reflect a diet. And in our case, the isotopic measurements really matched the known diet for ichthyosaur.
So it confirmed that what people thought they ate, they actually did eat.
Yeah, it confirmed that the cholesterol was really coming from the ichthyosaur, and it confirmed that it has cephalopod and fish diet. So basically, it was eating octopi and fish.
Right, but it's pretty amazing to actually have organic matter lasting 180 million years to actually be able to look at it now.
Yes and no, in the way that organic matter being preserved at up to a certain degree is something quite common. For example, all petroleum products are preserved organic matter over time. It's like molecular fossil that we use in our car on a daily basis.
Yeah.
What is exceptional is we got some organic matter that was not altered. And that's the thing, like in oil and gas, in petroleum, the products are organic matter, but they've been altered through times, while in our case, cholesterol is directly related to the organism. It's been produced by the organism and preserved in the same way. It's not been changed over time. That is a really exceptional and exciting finding on the biomarker aspect.
You've kind of finished this work and you've just submitted your PhD thesis, is that correct?
Yeah, I've actually submitted it a while ago, but as I had a baby in between, it took me a certain amount of time to finish my corrections, and I'm recently completed my PhD, and now I'm a doctor.
Thank you for joining us on Lost in Science. Doctor...
thank you again. Thank you for inviting me.
That's all we've got time for on this episode of Lost in Science. Thanks for tuning in and joining us. Lost in Science is recorded at the studios of 3CR in Melbourne and broadcast across Australia on the Community Radio Network. If you want to talk to us, talk back to us, you can get in touch. We have a Gmail account, lostinsight@gmail. You can also find us on Twitter and on the Facebook. And if that's not enough Lost in Science for you, you can always tune in again next week, where the team will once again get lost in science!
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.